In this module, I'm going to talk about pKa and how they're derived, and we're going to use these to estimate the extent of protonation of an acid in water at different pH. So here's a typical acid-base reaction. This is an ammonium. We've seen an example of that in the past. The R is just a group of carbon and hydrogen. Nothing unusual. This means that we can use any groups of carbon and hydrogen. We'll use this a lot over the course of the semester. So that ammonium is the acid, water is the base again, and that's what we've been using in all of the previous examples. We're going to have the conjugate acid, which is an amine, the RNH2, and the conjugate base, which is the H3O+, and this is going to be in equilibrium. So the KEQ, as I've mentioned before, is going to be it's going to be a fraction. It's going to be the product of the concentrations of the products. On the numerator, and in the denominator, the product of the concentrations of the reactants. And so this is old stuff from general chemistry that you ought to know. We're going to do a little bit of manipulation here. We're going to multiply both sides by H2O, and we're able to do this because we've only used trace amounts of acid, so the concentration of water has not changed in any consequential way. So we're going to multiply both sides by the concentration of H2O. This is going to allow us to cancel out the H2Os on the right side in the numerator and denominator. And we're going to have the concentration of H2O times KEQ equals the fraction at the right-hand side. And so we're going to call the concentration of H2O times KEQ. We're going to give that a special name. This is the Ka, this is the K acid. This is the kind of equilibrium we have when an acid gives up a proton in water. We're going to call that K acid. And then we're going to take the negative log of Ka, and we're going to have to take the negative log of the fraction at the right-hand side, so I've indicated that as well. And that negative log of Ka we're going to call the pKa. So that's the origin of pKa. It's looking at the equilibrium between an acid and water as the base, making the conjugate base, and hydronium in the reaction. We're looking at that KEQ, and we're massaging. We're arithmetically changing KEQ by just a little bit because we're assuming that the water concentration hasn't changed. So the pKa is really essentially it's the KEQ times the concentration of water. So if we wanted to convert Ka into KEQ, all we'd have to do is divide Ka by the concentration of water, which is 55, and that would be the same thing as KEQ. So in any case, that's the pKa. We're going to do a couple of things about this. First of all, we're going to recognize the following, that the equilibrium we're talking about at the very top, that the KEQ in that equilibrium is constant. That's why we give it the name K. It is constant. It doesn't change even though we change the components, that is the acid, the base, or the conjugate base and the conjugate acid. We can add some of those components to this, and KEQ will shift one direction or the other. This is something that you learned and we called Le Chatelier in the past. So we can add H3O+, and this is going to shift the equilibrium to the left according to Le Chatelier. And the reason it's going to shift the equilibrium to the left is that essentially if we add H3O+, we're increasing the amount that's in the numerator. The concentration increases, and therefore we're going to have to decrease the RNH2, that is the other component up there, in order for the KEQ to stay the same, or for the Ka to stay the same. This is pretty much saying the same thing. So we're going to shift the equilibrium direction one way or other because the KEQ has to remain constant. If we add OH-, this is going to decrease the amount of H3O+, and we're going to shift the equilibrium to the right, and that's because KEQ has to stay the same. If we add H3O+ or OH-, we're going to be changing the pH of the solution, and so essentially we could also say that we can decrease the pH, which is the same thing as increasing the H3O+ concentration, and it'll shift the direction one way or the other. So keep in mind, we're able to shift this equilibrium one direction or other depending on what the pH of the solution is. And so let's shift this equilibrium to the point where the conjugate base is in equal amounts as the conjugate acid. In other words, a different way to say this is that the acid is half deprotonated. we look at the RNH3 plus, half of that has become the conjugate base. Those two are in equal amounts. So I'll sometimes say the acid is half deprotonated. That simply means that we have equal amounts of acid and conjugate base. So when that happens, let's look at the expression at the bottom, the pKa expression. Not at the bottom here, but the bottom of the equality expressions that we have above. When the RNH2 concentration is equal to the RNH3 plus concentration, those two cancel out. So when those two are the same concentration, pKa equals the negative log of H3O plus. The negative log of H3O plus by definition is pH. So when the pH is the same as the pKa, that's when the acid is in the equal concentration with the conjugate base. What does that tell us? That tells us for the acid up above, in this example, this is an ammonium acid. We saw an example of this in the previous presentation. But the pKa of that acid is about 9. So at pH of about 9, we have equal amounts of acid and conjugate base. And so that allows us to predict the protonation state of an acid and its conjugate base in water. So at pKa, so the pKa of the ammonium is 9, therefore at pH 9 we have equal amounts of the acid and the conjugate base. What happens if the pH is less than 9? And this is what happens when the solution is more acidic. When it's more acidic, we're going to be favored to the left. We're going to push the equilibrium to the left, so we're going to have more acid than we have conjugate base. So the left side is going to be favored. So what happens at pH of 8? Well, at pH of 8, we've increased the H3O plus concentration by a factor of 10. The pHs are logarithmic, and so pH of 8 is 10 times the H3O plus concentration, 10 times the H3O plus concentration as that of the pH of 9. And so we've shifted the H3O plus we've increased it by 10. That means that let's look at the middle expression above, the one that begins with the arrow that points to the Ka. We've increased the H3O plus concentration by a factor of 10. That means that ratio of RNH2 concentration divided by RNH3 plus, we're going to have to decrease that ratio. In other words, we're going to have to increase the RNH3 plus. We're going to have to increase that 10 to 1 versus the RNH2 concentration in order for the KEQ or the Ka to stay the same. So that means we'll push the equilibrium 10 times over in the direction of the acid, the RNH3 plus. In other words, we have 10 times more RNH3 plus than RNH2 if we have 10 times more H3O plus concentration. And so we can think about what happens if we change the pH to 10. If we change the pH to 10, and we're comparing this to pH of 9, where the acid and the conjugate base are in equal amounts. If the pH is at 10, then we've decreased the H3O plus concentration by a factor of 10, and that means we had to increase the RNH2 concentration by a factor of 10 versus the RNH3 plus. And so I'm looking at the middle expression up there, and I'm saying I'm increasing the H3O plus concentration by a certain amount, and therefore the ratio of the RNH2 concentration divided by the RNH3 plus concentration has to shift by some number so that the KEQ stays the same. And we should be able to figure out what the protonation state of an acid is at specific pHs. These are estimations of acid-base reactions in water, where water is the base in these reactions. And so we can tell how protonated an acid is. And that's going to be very important for protein and amino acid chemistry. So you'll need to be able to do this on exams. We certainly will have questions that relate to this. So in an acid-base equilibrium, the KEQ does not change. We may change the compositions, but the amounts of the different components in the equilibrium are going to change, so that the KEQ does not change. KEQ remains a constant. And so the equilibrium can be shifted to the left or the right depending on the pH. The acid and the conjugate base are in equal amounts when pH equals pKa. If the pH is 1 unit greater, that means it's 10 times less acidic. That's going to shift the equilibrium to the right, and it's going to increase the ratio of the conjugate base to the acid by a factor of 10. And that's it for this module.